Okay. Am I audible? Hello.
Yes, sir.
So, is it,
দাদা ভিডিও বলছি, সরি, রেকর্ডিংটা অন করেছো?
uh,
ঠিক আছে, ঠিক আছে।
so we start with some group action. All of you know what is group, what is first isomorphism theorem, etc. So I will start with group action. Then Silo theorem and etc. Definition: an action of a group G on a set S is a function or mapping G cross S equals to Gx for all such that number one, identity Gx equals to x for all x belongs to S. Number two, G1 G2 x equals to G1 G2x. Observation: let G be a group. I write when such an action is given, we write that G action is. Let G be a group that acts on a set S. Let or I write Carl is subset of S cross S such that x Carl is defined as x dash if there exists G belongs to G such that x equals to G x dash. Then is an equivalence relation. Check relation on S. Let OX equals to class of X for X belongs to S. Therefore, OX equals to, what is the class? OX equals to GX, such that G is called orbit of S, and GX is those G belongs to G such that Gx equals to X, fixes X. If it is defined as this, so OX is defined as this. If G1 G2 belongs to G, then G2 inverse G1 of X equals to inverse G1 X equals to G2 inverse X equals to now X, as G2X equals to X, this simply G2 inverse G2X equals to G2 inverse X. This imply G2 inverse G2 X equals to G2 inverse X. This implies X equals to G2 inverse X. Therefore, G2 inverse G1 also belongs to Gx. This implies Gx is a subgroup of G. This subgroup is called G. This subgroup is called stabilizer of X or isotropic group. Or isotropic group of X. So now one observation is, or you can say theorem, note that let G acts on a set. G means G is a group, okay, set S. Then for X belongs to S, OX cardinal number of OX is index of Gx. Proof. It is very easy, simple. All of you know this. What is this? Let gamma be the set of all left sets of Gx G. Then OX to gamma, GX goes to GGX. Claim theta is bijective. Consider phi gamma to OX, GGX goes to GX. Then phi is well defined as GGX equals to, if two cosets are same, equals to G dash GX. This implies G dash inverse G belongs to GX. This implies G dash inverse G of X equals to X. This implies GX G dash X. Okay, so this is well defined map, and what happened? Phi compose theta. Sorry, theta compose phi. Theta is bijective, and what is cardinal number of OX equals to index, that is equals to actually cardinal number of gamma. Okay, so next observation, let theta acts on G. What is this? Theta acts on G. I write let us consider G cross G to G. Gx goes to GXG inverse. Check that it is a group action. It is a group action. This group action is called conjugacy action. action. Now what is OX? Gx G inverse such that, because the action is G, here G dot x equals to Gx G inverse. This implies cardinal number of OX is equals to number of conjugate element of X in G. Now what is stabilizer of X? Those G that is equals to centralizer of X. Okay, CGX. Now X belongs to, note that in this action X belongs to center. X belongs to center if and only if and only one. Now G can be written as disjoint union of OX distinct classes. So this implies cardinality of G equals to summation of cardinality OX, because it is equivalence class. OX intersection OY is empty. Distinct now I can now what is cardinality of OX is, if it is 1 by I denote it by a green star. By the green star by green star we have we have I write here this notation x equals to zg. center of group. Then one but as in this action. Therefore, what is the result? Sorry, this is small x. This is called class equation. All of you know. Then this is called G. Okay. Another observation is, I should write another page. In another page 2. So note that, also here note that number of x in G is Ox equals to, so centralizer index of centralizer is the number of conjugates of x in G. Okay, this is very important. Now so similarly, if I ask what is the number of conjugate subgroup, what is the number of conjugate subgroup? Can you say? Okay, let what has happened is, let G be a group and H subgroup of G. Let uh, let X belongs to, or I write S, let G belongs to, and G belongs to G. The subgroup GHG inverse is called a conjugate subgroup of G. Let S be the set of all subgroups of G. Now I define H. I define G acts on S by S. G H goes to G H G inverse. Okay, check that this is an action. This is a group action. Similarly, what is OH? Such that the simpler cardinality of OH, number of conjugate subgroup of subgroups of H. Now what is GH? Those G belongs to G such that H. So what is this? Normalizer of H. Therefore OH cardinality equals to G NGH. Thus G colon NGH denote number of conjugate subgroups of H in G. Okay. Another observation, let for no let for any set S define or let AS be the group of permutations on S. That means S to S all set of all bijection and composition is under composition. all bijection under composition, it is a group, and this is group of permutation only. Let or suppose G acts on S. I write theta. This action will induces a group homomorphism theta tilde G2S more goes to tau G, where tau G S to S, X goes to GX. And my question is, where tell me a criteria where theta tilde is injective, so I can embed theta tilde G as S. আমার একটা কেস বলতে পারো, অ্যাকশন বলতে পারো যেখানে থিটা টিল্ডাটা ইনজেক্টিভ হয়ে যাবে? Tell me a group action where theta tilde is injective. At first I see that tau G is bijection. Tau G X equals to tau G Y for XY S. Gx equals to Gy. G inverse Gx equals to G inverse Gy. Y. So tau G actually lies in AS. So this is no problem. And tau theta G1 G2 tau G1 G2 of X G1 G2 X now it is a group action. Tau G1 G2 theta tilde is I should write theta tilde. Theta tilde is a group homomorphism. If you have any question, please ask me. So theta tilde is a group homomorphism. Now I want to a particular action. Take S equals to G and theta is the usual group operation. That is dot group. I write operation, not operation, usual group multiplication. That is better. One can take addition. Operation is better. So dot G cross G to G. Then this action will induces a group homomorphism dot, I write theta tilde, or I'll give no name. Group homomorphism G to H. No, I write theta tilde. What is kernel of theta tilde? Tau G. Kernel theta tilde is those G belongs to G such that tau G equals to identity. Now tau G of x equals to x for all x belongs to G. Tau G equals to identity if and only if particular tau G of identity G equals to identity G. This implies G identity G equals to identity G. So kernel theta tilde is EG. Hence theta tilde is injective. Is injective and G is a subgroup of H. Moreover, if cardinality G is n finite, this implies AG is isomorphic to Sn. Actually equals to Sn, subgroup of Sn. So this is called Callis theorem. So I can embed any finite group to Sn. So there is another representation. I can embed any finite group to some matrices group. This line is called representation theory. And this is better. As I note that very interesting observation. let G be a group. What is this? G be a group. Then consider consider just here I considered usual group action. Now I consider I should write this way. Take case 2, special case, another case. I should write another case. Take S equals to G and the action is conjugacy action. So these action will induce group homomorphism G to AG. What is AG? AG I also write that ORT G, another notation. AG and ORT G are same. What is so why ORT? Whenever I say that S is a set, then there is only bijection S to S. But if S is a group, then for bijection you can say that kernel of this is in trivial, this type of matter. So ORT G is group of isomorphisms. Group of isomorphism from G to G. This is called automorphism. G goes to tau G. Tau G of X is Gx G inverse for all X belongs to G. Now theta tilde. So what is kernel theta tilde? Kernel theta tilde, can you say anything? Those G
Center
belongs
of
to
G.
Such that tau G
Center.
is identity, right? Now tau G is identity. This imply tau G of X equals to X for all X belongs to G. So I can write Gx G inverse equals to X for all X belongs to G. So what is this? Gx equals to Xg for all X belongs to G. So what is this? Those G such that Gx equals to Xg for all X belongs to G. What is this? This is center, right? Right. So I can write that G quotient ZG is a subgroup of ORT G. The first isomorphism. So these are some trivial observations. Now image theta, element of, just notation, or I said right definition, element of image theta tilde are called inner automorphism. Automorphism. In this case, obviously, in this action, I should write in this action. In the conjugacy action are called inner automorphism. So image theta tilde will denoted by in G or inner set of all inner automorphisms. It is look like tau G. All of G. So G mod ZG, hence isomorphic to in G, that is subgroup of odd G. Okay. Another observation is, suppose H is a subgroup of, let H, observation, H be a subgroup of G and S be the set of all left cosets of H in G. Now G acts on S by left translation. That action actually called left translation. What is G? And if it is XH, it just simply goes to GXH. Check that this is a group action, and this action is called left translation on the coset of all left cosets. As this is a group action, and this action is called the set of all this action is called the left translation on the set of H. Okay, just to take this. So this action, this action will induces a uh, group homomorphism theta tilde G to AS what is the map used to tau G? What is tau G? S to S XH goes to GXH. Now what is kernel? Again I am interested in kernel. Suppose G belongs to kernel theta tilde. This implies tau G equals to identity on S. This implies tau G of XH equals to XH for all XH belongs to S. This implies GXH XH belongs to S. In particular, or I write this imply. I just put X equals to identity. GH equals to H. This implies G belongs to H. So I see that kernel theta tilde is subgroup of H. This is just observation. Okay. If I take this an action which is left translation on set of all left coset, then kernel theta tilde is subgroup of H. So I am taking various action and observing the kernel of theta tilde. All of these are very related to Sylow's theorem, etc. These are all very important observation. Okay. Now suppose particular case, suppose G is a finite group. I write why it is not erasing. Suppose coordinate G is n equals to n that is finite group, and H is a subgroup of G with H with G colon H equals to P, comma a list prime that divides n. A list prime that divide order of G, that is n. Then H is normal. All of you know this result. So we have, what is the observation? Kernel theta tilde is subgroup of H. Just from I write it, this is by this blue star. So G G colon kernel theta tilde equals to G is to H H is to kernel theta tilde. This is okay. Now G colon kernel theta tilde is subgroup of AG, oh sorry, AS. AS. What is happening? AS. This is equals to SP because what is the G colon H equals to P, so cardinality of S is P. So it is index P. Therefore, set of all left coset I have here AS, that is SP. So G colon kernel theta tilde is subgroup of AS, that is SP. So G colon kernel theta tilde order divide by Lagrange theorem SP, that is P factorial. Now what is this? G is to H, H is to kernel theta tilde divide order of P factorial. That means H is to kernel theta tilde divide P minus 1 factorial. If H is to kernel theta tilde is not equals to 1, take a prime Q such that Q divide, take a prime divisor of this Q with Q divide H colon kernel theta tilde. This imply Q should divide, now Q divide H colon kernel theta tilde, H colon kernel theta tilde divide P minus 1 factorial. So Q should divide P minus 1 factorial. This imply Q less than P. Now Q is the divisor of H colon kernel theta tilde. And H colon kernel theta tilde divide by this line G is to kernel theta equals to this. I should write it by blue star. Alright, double star. Divide divide, what is this? G is to kernel theta tilde by dy, and G is to kernel index divide order of G by Lagrange. Combine all of this, combining it is G, Q, it is G. All results we get Q should divide order of G. Contradiction: as Q is less than P and P is the least prime that divide order of G. Therefore, so our assumption H colon kernel theta tilde is not equals to 1 is wrong. Therefore, H colon kernel theta tilde is equals to 1. This implies H equals to kernel theta tilde. Now, kernel of a group homomorphism is normal. This implies H is normal subgroup of G. Okay. Okay. If you have any question, then ask me. Bolo. If you have any question, please ask me. Bolo. If you have no question, then I will stop here, and next day I will go through Cauchy and Seiler's theorem, then semi-direct product, and this way. Okay, and some problems also. In Seiler theorem there are so many plenties of problems. No one has any question. Okay. So here I am giving a definition, and just see that this makes definition of group action. Then I see that this is a curl x related with x prime if and only if there exists G belongs to G such that x equals to Gx prime. So this is an equivalence relation. Then I define orbit, that is class X, equivalence class, and stabilizer. Nothing, and rest of them I take any various action and investigate what is kernel, what is the orbit, what is stabilizer, etc. Nothing. So there are 2-3 special type of group actions. One is left translation, another is conjugation, another is left translation on set of coset, and another is conjugation on set of all subgroups. Then, and investigate what is kernel theta tilde, what is Gx stabilizer, what is the orbit, etc. So there are some small applications on class equations on p groups. I'll discuss in next day. Okay. Okay.